Ghosh. I am from Chemistry Department of Georgia State University. First of all, I would like to thank SERMACS for giving me this opportunity for presenting my research here. In today's talk, I would like to discuss about this topic, which is the path to the triplet state in LOV domains. So in our lab, we do computational chemistry where we are interested in understanding the photophysical processes of biologically important molecule which responds in presence of light. These are called photoreceptors. There are very few families of photoreceptor proteins which include phytochromes, rhodopsins, xanthopsins, cryptochromes, phototrophins or LOV domains, and blood proteins. Currently, we are interested in understanding the photophysical processes of LOV domains after absorbing light, for which this flavin molecule is the chromophore which is responsible for the absorption of light. Now the question is why we are interested in such system. LOV domain shows various photophysical processes upon absorption, and each individual photophysical process of LOV domain has its own industrial application. As for example, it absorbs in the blue region by which it excites to its first singlet excited state, and from there it can return back to the ground state via fluorescence. The fluorescence probe of flavin can be used for bioimaging, and also it has other applications too. Again, from S1 it can populate one of the triplet state via intersystem crossing, and after this process it generates very reactive singlet oxygen which can be used for controlled singlet oxygen production. Flavin can also undergo redox reaction, and the ability of flavin undergoing this redox reaction within the protein environment can be used in the field of optogenetics. In my postdoctoral research, I was particularly interested in understanding the mechanism of intersystem crossing within the LOV protein. We know any electronic transition between two states having different spin multiplicity is spectroscopically forbidden. But particularly for LOV domains, it has been experimentally observed that this triplet formation can happen in a nanosecond time scale with 60 to 70% yield. The question is how and why. Now, as it is an excited state photo process, therefore we need to know what type of lower lying singlet as well as triplet excited states are present for flavin, and what will be the effect of environment on those singlet and triplet excited state. To understand this, we have generated a map. This map is called Electrostatic Spectral Tuning Map, and this map can be used as a starting point for understanding the effect of environment on those excited states. So what is this map? Let's say you have a molecule. The molecule has a van der Waals radii and the corresponding van der Waals surface. We put a positive charge of 0.1 electron magnitude at each 1 angstrom square of the surface, by which we get around 450 to 500 number of points, and at each point we perform vertical excitation energy calculation including some low-lying singlet as well as triplet excited state, and finally we get these points, among which some of the vertical excitation energy decreases. This means wavelength increases. This we call as redshift, and we have indicated those regions with red color. And some of the vertical excitation energy increases. This means wavelength decreases. This we call as blue shift, and we have indicated those regions with blue colors. And finally, by interpolation, we get this map. Now, higher the color intensity of this map, higher is the change in vertical excitation energy due to presence of that positive point charge, and higher will be the sensitivity for that particular state to the environment. And consequently, lower is the color intensity of the map, lower will be the change in vertical excitation energy due to the presence of that point charge, positive point charge, and lower will be the sensitivity for that particular state to the environment. So, to understand the same effect for flavin, we have generated this map for at least 3 singlet and 3 triplet lower lying excited states. As for example, these two are the ESTM for first singlet and first triplet excited state, which are pi to pi star in nature. And from the color intensity of the map, it is very it is kind of clear that these two excited states are not that sensitive to the environment. We have also generated the map for second triplet excited state and the corresponding singlet excited state, which are n to pi star in nature. Here this n orbital means it's a lone pair or non-bonding orbital having electron density mainly on the n5 nitrogen atom. Next we have generated the same map for third triplet and the corresponding singlet excited state, which are again pi to pi star in nature, but here this initial pi orbital is different from the pi orbital which was involved for S1 and T1. And the main important thing is all these four excited states are highly sensitive to the environment, which is clear from the color intensity of their corresponding map. So now we know how these excited states are going to behave in presence of the environmental charge. So let's take a pause and think what was our actual aim. Our aim was understanding the mechanism of intersystem crossing within the LOV domain. What do we need for that? We need at least two excited states. One is singlet and another is the triplet. Now here the first singlet excited state, that is optically active pi star in nature. And we know after absorbing light any molecule occupies the most bright excited state, which is the S1 here. And next we need other a triplet state. Now I just introduced that we have three low-lying triplet state, among which this T1 and T3 are pi star in nature, T1 and T3 are pi star in nature, and the T2 has a different excitation which is n to pi star in nature. Now there is a rule, L-Schwab rule. This rule says us that the rate of intersystem crossing will be significantly high when this radiation-based transition involves a change in type of molecular orbital. Specifically, transition between pi star and n pi star will be significantly high, but if the transition occurs between pi star to pi star, the probability of that transition will not be that high. This means the most two important state for efficient intersystem crossing for flavin should be S1 and the triplet n pi star state. Now, to understand the effect of environment on these two excited states, we have extended our system from gas phase flavin to flavin in solution, for which we took polarization continuum model with the dielectric constant of water, which we will call as PCM water model, and also to a typical LOV protein which is AT-LOV2. And for the gas phase and PCM water, we have used purely quantum mechanical calculation. And for the protein, what we did is that we treated the most important part of the protein, that is the flavin, with quantum mechanics, and the rest of the part with molecular mechanics, which is hybrid UMMM method. Now with this method and for all these systems individually, what we first is that we calculated the vertical excitation energy of those low-lying singlet and triplet excitation. Here is the low-lying excitation of gas phase flavin. Now if we look at the each excitation, how it is changing in different environment, we have noticed that T1 gets stabilized from gas phase flavin to solution to protein environment. S1 also shows the similar effect as T1 but with a slightly blue shift within the solution. Now the most important triplet state, that is the triplet n pi star state, that gets destabilized within the solution but gets stabilized within the protein environment. And also the other triplet pi star state, we should also be highly sensitive to the environment according to the ESTM which I showed earlier, that gets stabilized within the solution but gets destabilized within the protein environment. This means these two triplet pi star state and the n pi star state are showing different behavior in various environment, which is clear from their ESTM map if we look at the ESTM map again. And also the other singlet n pi star state that shows the similar behavior as the triplet n pi star state as expected. So now we know how these excitations are getting stabilized or destabilized due to presence of solvent molecule or the environmental charge of the protein. But what will be the pathway? pathway for the intersystem crossing. How the S1 state and the triplet n-pi star state are crossing with each other. To understand this, we took the minimum energy structure of these two important states and we have generated some point by linear interpolation and extrapolation of Cartesian coordinate like this, and we have performed vertical excitation energy calculation including all those low-lying singlet and triplet excited state at each point, and finally we get our one-dimensional potential energy surfaces of flavin at different environment. So here is our S0, then we have T1, then we have the bright S1 state, then we have the triplet n-pi star state, and then we have the other triplet pi star state and the singlet n-pi star state. So what is the pathway overall? The overall pathway is after photoexcitation, it will occupy the bright S1 state, then it will populate the triplet n-pi star state via intersystem crossing, followed by internal conversion with the T1 pi star state. But the most important thing which we should notice here is that irrespective of the environment, we do have the intersystem crossing between the S1 and the triplet n-pi star state. So then what is special about the protein here? To answer this, we took a look at the minimum energy structure of these two important steps and we compared them in different environment, and we have seen that within the solution, this triplet n-pi star state minimum is 4.61 kcal per mole higher in energy than S1 minimum. But within the protein, this triplet n-pi star minimum is 1 kcal per mole lower in energy than the S1 minimum. This means protein environment is somehow stabilizing the triplet n-pi star state. But the question is how? So to understand that, one of my lab mates, Stephen, he generated a map. This map is called protein electrostatic projection map. What is this map tells us about? This map tells us how flavin chromophore is experiencing electrostatic potential due to presence of the nearby amino acids of the protein. In this map, this red color means flavin is experiencing negative potential from those regions, and the blue color means flavin is experiencing positive potential from those regions. Now if you look at these three maps, the first one is the front view of the flavin, the second one is the back view of the flavin, and the third one is the bottom view of the flavin if you orient the flavin like this. And then you will notice that near the N5 nitrogen atom, flavin is experiencing a strong negative potential by all this region. Due to this interaction between the electron density of the N5 non-bonding orbital, which was involved in that triplet n-pi star state, and also the interaction of the negative potential whatever amino acid are present here, due to this negative interaction, the energy of the N5 non-bonding orbital increases, which ultimately stabilizes the triplet n-pi star state. Now the question is, what are those amino acids which are playing key role here? To answer, we have investigated that also, and if we turned off the cysteine 426 from here, then that red patches from the front view of the flavin will be not here. If we turned off the phenylalanine 470 from here, then the red patches from the back view of the flavin will go away, and if we turned off the glutamine 489 from there, then the red patches from the bottom view of the flavin will be not there. This means these are the three amino acids whose electron-rich side chain are projecting a strong negative potential to the N5 nitrogen atom, due to which it is finally stabilizing the triplet n-pi star state in such a way that it is getting involved for the efficient intersystem crossing with the S1 within the protein environment. So with this note, I would like to stop here, and I would like to thank my supervisor Dr. Ghosh for his help and support, and all other lab members of our lab, and especially Stephen for helping me in this project. Thanks for listening. Thank you.